Why does divide and conquer even work? Instead of manually going through and doing the work step by step, divide and conquer makes us recursively break the problem up, and somehow, almost magically, merging those pieces together gets us the same work done faster. To me, this never felt motivated. That is, until I looked at sorting. On the left, we have the array we're going to be sorting. And on the right, we have a table that'll be recording every comparison the algorithm does. For example, when we write the comparison symbol in this square here, it means the algorithm has learned that the fourth element, 68, is greater than the sixth element, 36. Note that we only have entries on this upper right triangle. We only care about unique comparisons, which each come from a unique pair of elements in our input. We'll take a look at insertion sort's worst case, a reverse sorted list, to see why it's in O of n squared. Let's run it now. As you can see, insertion sort in its worst case is forced to manually compare every pair of elements, which is why it's in O of n squared. And now, to answer our question from the beginning, why does divide and conquer speed up sorting? Transitivity. If A is less than B and B is less than C, then you automatically know that A is less than C. This means that sometimes, after an algorithm has already done some comparisons, a manual comparison gets us a free one too. And sometimes, we even get multiple comparisons with one computation in a chain reaction. And to show you this in action, here's merge sort on a randomly ordered input. I'll color the information we manually compute red, and the information we get for free from transitivity blue. This is the secret of merge sort's speedup. Merge sort uses transitivity through divide and conquer to guarantee it never has to manually compute every pair of elements, no matter the input. As far as I can tell, this happens with every algorithm that uses divide and conquer to improve its lower bound. For example, Strawson's algorithm takes advantage of the distributive property, much the same way that sorting algorithms use the transitive property. Other problems also use the transitive property to power a divide and conquer algorithm, like the closest pair of points problem. But for divide and conquer and other algorithm design techniques, the perspective to keep in mind is this. It's interesting, and maybe even useful, to track how information is accumulated during the course of an algorithm.